I am a protector, exploring the expanses of space to keep our planet safe, and all the species that call it home. I am a healer, giving doctors the vision to create amazing new cures. And using the heart's own magnetic field to diagnose itself. I am a guardian, searching a mountain of data to keep us safe when we travel, and a sea of people to find a lost child. I am a helper, powering autonomous machines that simplify our lives. Capture our greatest adventures. And make us whole again. I am a visionary, enabling taxis that don't need steering wheels, and those that don't need roads. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere. Ladies and gentlemen, please welcome NVIDIA founder and CEO, Jensen Huang.
GTC China, 大家欢迎。And welcome to Suzhou for a record GTC China. This room is packed. It's so great to see all of you. I have so much to tell you today, so let's get started. My talk today will be in 3 chapters. The first chapter is how we are going to reinvent computer graphics. The second is how we're going to reinvent the future of computing. And third is how AI will automate the world with autonomous machines. These 3 chapters, I have much to share with you, and there's so much going on here in China, so let's get started. 15 years ago, we invented the programmable shader. The programmable shading GPU revolutionized computer graphics. Almost everything that you see today in video games, in game consoles, in cell phones, the computer graphics was made possible as a result of the programmable shader that we invented 15 years ago. For the last 10 years, we've been working on reinventing computer graphics. And Turing, our newest GPU architecture, is the result of that incredible work. Turing is a complete reinvention of how real-time computer graphics will be done. Whereas Pascal, our last generation GPU, had one basic processor called the programmable shader, the Turing GPU includes 3 processors. One processor for classic programmable shading that we invented 15 years ago. A second processor dedicated to ray tracing, to simulate the properties of light as it bounces all over a room illuminating an object, changing tone maybe, and ultimately reaching your eyes. Billions of rays per second are bouncing all over the room so that the image could be beautiful and realistic. We call that the RT core. Real-time ray tracing made possible for the very first time. And then the third processor is an invention of ours called the tensor core. The tensor core makes possible deep learning neural network artificial intelligence to be operated at incredible speeds. The tensor core, the RT core, and the programmable shader makes up the Turing processor. If you look at the computation, of these processors, the difference is dramatic. The programmable shader of Pascal, this is the Titan XP, the highest end version of Pascal, is almost 13 teraflops of computation. However, Turing has an independent floating point as well as integer pipeline, 14 teraflops and 14 tops each. And then in addition to that, the tensor core processor for deep learning and artificial intelligence of 114 teraflops. We're basically increasing the computation of Turing over that of Pascal by nearly a factor of 10. It's an incredible speed up. The tensor core will be used for all kinds of amazing things that I'll show you. First of all, of course, it'll be able to generate images in a way that isn't possible today. It can enhance images. It can even make characters animate in artificial worlds, very realistic way. And so Turing, a brand new processor with an enormous amount of computational capability in 3 processors, the shader, the ray tracing engine, and the tensor core processor. As a result, we're able to create special effects and render images that were simply not possible before, doing reflections and beautiful shadows. And then a new technology we call DLSS. DLSS is a neural network model that runs on the tensor core. We train this neural network model. We train the neural network model to take an image and make it more beautiful. You give it an input, as we do here, maybe a lower resolution input. Because this neural network model has been trained with an enormous number of examples of beautiful images, it knows how to enhance that image to make it even more beautiful than when you first started. Using that technique, we could render a smaller image, conserving our computation capability, and use the 114 teraflops tensor core to enhance that image, increasing its resolution, doing super resolution, and as a result, improving quality while improving performance. This new method of computer graphics has enormous potential. I want to show it to you. What I'm going to show you here is the Justice game. This is the leading MMORPG here in China. This game is beautiful, and we're going to make it even more beautiful. I think Calvin?
Hi, this is Calvin.
Hi, Calvin. How are you doing?
I'm fine.
First of all, this is our last GTC of the year.
Sure.
I would like to thank all of you for your hard work.
Thank you, Jess.
Ladies and gentlemen, this is the engineering tech band of NVIDIA.
Thank you. Thank you, everyone.
We have been all over the world together. We're like a band. You know? We're like a band. All right, Calvin, take it away. Let's show us what you're going to show us. Okay.
Okay.
Wow.
Okay, this is a live demo. The demo is using DLSS to render at 4K resolution.
Okay, so we're looking at a 4K resolution. This is with ray tracing on. One of the things that you notice is the beautiful reflections. The way that video games do reflections today is a, if you will, a technique, a simplification called screen space reflection that we invented several years ago. If the image is on the screen, we can map it into the reflective surface. And as a result, it could be shown as a reflection. However, if the image is not on the screen, it cannot be shown as a reflection. The beauty of ray tracing is that because it's bouncing light all over the environment, it doesn't matter if the image is on the screen or not. And so Calvin is going to show you here, right here. Notice this image right here, this part of the cart is not seen on top, yet the reflection is here. And Calvin, if you could turn that off, notice without ray tracing, and then show me with ray tracing. And notice here, show me without ray tracing, and show me with ray tracing. And so, before ray tracing off, RTX off, notice here, and then on. Can you see that? Beautiful, right? And it's so natural. Even the ripples on the water is behaving naturally. I'll show you more. Okay, Calvin, let's go. This is all being rendered in 4K. We'll stop here. Oh, look at this reflection. It's so beautiful. Now, everything here looks very natural. Everything here looks very natural. But let me show you what today's video game looks like without RTX, without ray tracing. This is what it looks like. This is the technology we invented 15 years ago. And I'm still very proud of it. But clearly, it is wrong. Clearly, there are many things that's missing. And clearly, it could be much more beautiful. And so now, ray tracing on. Look at under the bridge. It's called caustics. Light is shining, reflecting off of the water, up against the bridge, and it's causing that ripple that it's called caustics of the water. Turn it off. Turn it on. Look at the reflection of this light against the boat. Turn it off. Turn it on. Turn it off one more time. Oh, it's so much joy, right? So much technology. And look what happens. We can create reality. Okay, show you one more. We have the best job in the world. We could apply all this great technology to bring joy to people. And if we do a good job, then people could tell wonderful stories. Look at the reflections on the ground, on everything. It's just all natural. All happens by itself. Look at this. Notice the reflection of the metal. This is rough, and so the reflection is rough. This is shiny, so the reflection is shinier. And look at the front, okay? And notice this. Even notice this. This little tiny piece of metal is reflecting the environment. Okay, go ahead. RTX off. RTX on. RTX off. RTX on. This is, you know that Tom Cruise movie? This is with me without me. Without me. With me, without me. Not bad, right? Okay, Calvin. That's we could sit here and play all day. Keep going. Isn't that beautiful? It's all dynamic, it's all moving, and it's completely easy to do because it's behaving according to the laws of physics. Everything just works all by itself. The software programmer's job is much easier, in fact. Okay, ladies and gentlemen, thank you. RTX.
Thank you, Jensen.
Calvin, thank you.
Thank you, Jensen.
Good job. Now, one of the things that you noticed was we were rendering at 4K. We're rendering at 4K. There are two technologies. Remember, there's the RT Core ray tracing, and then there's the Tensor Core, the deep learning tensor processing, 114 teraflops. And so we're rendering, in this case, this is rendered in 4K. This is rendered 4K TAA anti-aliasing, temporal anti-aliasing. So this is 4K, but this was only rendered to 1440p. Half the resolution, and then two artificial intelligence models were used. The first model is to enhance the image at 1440p, and the second is to expand the image, to super res the image, to create 4K, and to do so in such a way as to retain and maybe even enhance the visual quality. As a result, DLSS, the Tensor Core, is using 114 teraflops to render the image when this is only 14 teraflops. Almost 10 times more computation can be applied to generate that image. As a result, the quality is high and the image quality and the performance is high. That's called DLSS. In combination, this is what it looks like. This is what Pascal does. The Pascal 1080 Ti is the highest end GPU at $699. $699. This is the RTX 2070 at $499, $200 cheaper. And yet it's almost 4 times faster with next generation content. It's really quite amazing. This is the power of using 3 processors, programmable shader, RT Core, and Tensor Core combined to generate the next generation image. This is the first title that will have DLSS here in China. It's called the JX3. And let me give you some examples. This is the new GeForce RTX. Okay. This is the new GeForce RTX. And let me show you what it can do. GeForce RTX, even without ray tracing, we could use deep learning and the 114 teraflops Tensor Core to enhance our performance, just to enhance our performance. This is our top 2 high-end Pascal GPUs, $699, $699, and $499. Okay, $699, $499. This is what RTX looks like without DLSS. Without DLSS. So the 2070 is comparable to a 1080. The 2080 is faster than a 1080 Ti, and a 2080 Ti, of course, is much faster. This is without DLSS. With DLSS, on this title, it looks like this. Now look at that amazing performance improvement. That basically says a 2070 without ray tracing, can deliver performance at $499 that's higher than a 1080 Ti at $699. Pretty spectacular performance improvement. generational performance improvement. And so that's made possible as a result of RTX's Tensor Core processor. Now let me show you what this new GPU can do with a piece of a demo that we did together with Epic. This is really, really beautiful. And this was done to celebrate a 70-year anniversary. Let's show it to them.
The speed of light, a universal constant, never diminishing, never ending. "70 years of unrelenting progress. The Porsche 911 Speedster concept. The speed of light."
Isn't that incredibly beautiful, guys? That is not a movie. What you just saw is not a movie. This is completely in real time. What do you think? The reflections, the lighting, the shadows, it all just works. It's all ray traced. 10 gigarays per second. 10 billion rays per second, bouncing all around this car, creating this beautiful image. And look at this. This light is above the ceiling. It is not in this room. And yet the reflection is perfect, and the reflection off of the car is perfect. Nothing has to be done. It just has to be turned on. So this is the future of computer graphics, and imagine, this is the future of video games. After 10 years, the Turing architecture is going to reinvent computer graphics. Thanks, guys. Moore's law has come to an end. Moore's law has come to an end. For my entire career, every single year, the microprocessor got faster and faster and faster. Every 10 years, Moore's law predicted, and the industry relied on it, to improve performance by a factor of 100. Every 10 years, microprocessor performance improved by 100 times. For 35 years, for my entire career, that was true. For 35 years, Moore's law advanced at 100x every 10 years. The last several years, it has come to a halt. Now, to imagine this, for something as vital to humanity, the single most important instrument of society today, the computer, for the advancement to come to a stop, instead of 100 times every 10 years, let's say that it is only 2 times every 10 years, because it's only improving by a few percent per year. In 10 years' time, the industry will have a deficit, a shortage of computing power by 50 times. Or the cost of computers will increase by 50 times. Or the power necessary to run our data centers will increase by 50 times. Or we simply cannot have any more performance improvement. Moore's law coming to an end, is exactly the reason why the CapEx of data centers and internet companies are growing so fast. Because it is no longer possible to wait 1.5 years and the performance will double with no additional cost. And then the performance double, no additional cost. That trend has come to an end. That is the meaning of Moore's law. The meaning of Moore's law is that in the future, unless we do something different, unless we change the computing approach, the cost of computing will skyrocket. The power of computing will skyrocket. The implication to our industry is severe. I think that this observation that we made almost 10 years ago, when we started pioneering our approach called accelerated computing, is now common sense. Everybody now acknowledge Moore's law has ended. We must do something. We've been working on this approach for 10 years, and we've made enormous progress. In fact, our approach is not the easy road. It's called accelerated computing because general purpose computing, using C compilers, writing general purpose programs, was very flexible. That was its power. It was very flexible. To go forward, we did not want to lose the flexibility of general purpose computing, and so we added, and we did not remove the CPU. We added a special chip. We added a special chip whose job is to perform the very heavy workload, the parallel workload, the inside part of the kernel. But that is not enough. In order to accelerate the application, we have to completely redesign the software stack. The architecture of the chip, the system software in the system, the algorithm, and the applications all have to be optimized in order to take advantage of accelerated computing. Accelerated computing is a full stack problem. You cannot just put the GPU or an ASIC or anything underneath the software and expect it to improve the performance. You have to have the expertise to redesign the entire stack from bottom to top. Well, the only way to design an architecture from bottom to top is to understand it from top to bottom. And that's why NVIDIA is a software and an algorithm company. That's why we have so many computational mathematicians. We have to understand the software and the application and the algorithms from the top, and we have to understand how to accelerate it from the bottom. Over the years, we started from scientific computing, where the demand for accelerated computing and the feeling and the impact of the end of Moore's law was the greatest. We started with supercomputers. We started with scientific computing, where the simulation models were gigantic. It would simulate for many, many days, and the algorithms is simulating from first principle laws of physics. Here I showed you the Maxwell's equations. But over time, industry realized that the number of first principle methods to understand many of the world's phenomenons are simply impossible. There are too many things too complicated. For example, the human body. It's too complicated for there to be a Maxwell's equation. Weather simulation, too complicated because there's multi-physics. Social changes, too complicated. Your preference for movies, your preference for where to eat, those problems are too complicated for first principle analysis, and there are no laws and there are no equations to simulate that. And that's the advent of deep learning, machine learning, and what is known today as data science. So now we have scientific computing and data sciences driving our architecture. And then lastly, with any architecture, architectural discipline is vital. One of the greatest decisions that today's leading computing companies made long time ago is to keep instruction set architecture compatibility, to not break, to not have the discipline to chase everything, but to have the discipline to methodically advance the computing platform while retaining backwards compatibility and dedicating yourself generation after generation after generation to advancing the platform on the one hand, but taking along your entire install base on the other hand. We call that CUDA. CUDA is our architecture. It is backwards compatible, but forward extensible. We can continue to add more and more capabilities from CUDA 1 on Tesla, CUDA 3 on Fermi, CUDA 5 on Kepler. Does anybody in the audience know any of these generations? Any Fermi users in the audience? Any English-speaking audience? I feel, 我想我今天讲的话，大家听懂吗？还可以啦哈，不好意思。我的中文讲得很差，每一次来学一点，每一次来学一点。有一天，通通的 Keynote 讲英文的，讲中文的 ，OK？ 可是我想法是这样子，有一天我讲进去是英文，你们听到的是中文。下次来一定做完的，一定做得好了。This audience has no clue what I'm talking about. My band does not speak Chinese. Okay, so we have CUDA 5, CUDA 6 is Maxwell, CUDA 8, Pascal. Does anybody in the audience know Pascal? Okay. As you could see, notice, this is where all of you joined. This is in the beginning. We were growing the base, investing in the architecture. By the time Pascal came, the deep learning revolution started, and you could see the data science and all the data scientists and all the AI researchers and all the developers kicked our architecture into turbocharge. And it reached now 14 million downloads of CUDA in just last year. In just last year, 1 year, almost 6 million downloads. Unbelievable. Now we're on Volta, and then we're on Turing, CUDA 10. Each one of our generation, we keep adding to it. We keep adding to the capabilities. Each generation backwards compatible. So that now, the applications that are written, so many applications, will run on the entire install base. So the benefit of install base, so that developers can have the reach of many users. On the other hand, if the install base is large and the platform is capable and it's easy to use, then developers will be vibrant. Many developers, many users, a positive feedback system. And a positive feedback system looks a little bit like that. Every single year, it seems to grow even faster. The benefit of accelerated computing. We've been working on this, and we've been investing in this now for almost 12 years. As you could see, CUDA 10 already. Almost 12 years. And now the install base is quite large. You could see the results of our work. This is just this last week at supercomputing. At supercomputing, NVIDIA's presence and our achievement was very well recognized and surely felt. The highest performance computer in the world, called the Summit. 27,000 NVIDIA GPUs, 144 petaflops. This is equivalent to probably something like 1 million laptops. Okay, this computer could do something that 1 million laptops cannot do. 3.3 exaflops of AI. But we were also the number one in the world, the number one in Japan, the number one in Europe. We're 22 of the world's 25 most energy efficient computers. And one of the great achievements, 5 of the 6 scientific breakthroughs on high-performance computers were done on NVIDIA GPUs. And so I'm very, very pleased with that. And this year, the number of systems in the world's top 500 is starting to grow even faster. This year, almost 50% over last year, 127 systems in total. High-performance computing has confronted Moore's law. And the path forward is clearly accelerated computing. And after over a decade of investment, we find ourselves in a really great place to be able to help the industry forward. The second dynamic that's happening, the first dynamic is the end of Moore's law. And that's going to affect computers and computing industry all over the world. The second dynamic is artificial intelligence. The idea that we now have the ability for machines to learn, for machines to write software. It stands to reason that if a machine, a computer, were to write software that we cannot write, that this computer will have artificial intelligence. And to be able to write, to learn and to write software, to create software, the type of software that is created is only possible on computers like this. It stands to reason that a computer will have to be very powerful in order to write the type of software that no humans can write. However, as challenging as it is, the impact of artificial intelligence is so extraordinary. It is so extraordinary. And the reason for that is because we have now discovered a method of computer science that can solve problems that we had no ability to solve before now. We can now solve problems that are nearly superhuman when you think about it. Let me give you some examples. This is Alibaba. This is Singles Day, 11/11. $31 billion. $31 billion. If you had a store that does $10 million in one day, that's a very big store. It would need 3,000 stores to replace that one day. 3,000 stores. That's an enormous number of department stores, all done online. However, there are so many products on Alibaba's store. Millions and millions of products. How do we find the product that it should recommend for us to buy? So the recommendation system has to understand you. It has to be personalized shopping at a very extreme level. It has to learn from you so that it could make recommendations to you. It is believed that up to 30%, up to a third of the products that we buy on e-tail are recommended to us by AI. Not based on what we're searching, but based on what it recommends to us. And so, incredible power of AI. The benefit to society, of course, is that it's easy to shop, and of course, the number of stores and the acres of buildings are no longer necessary. But it has to be replaced by personalized shopping, which is only possible with AI. 8 billion people in China visit doctors each year. 8 billion visitors. 8 billion visitors. It is now possible to create an AI that is essentially your AI doctor. Your AI doctor. Your AI doctor could help reduce the number of visits that you go to the hospital. And if you were to go to the hospital, because the number of radiologists in the world is so limited, we can now use AI to augment, to accelerate, to reduce the burden on the number of radiologists in the world. Transportation, 2 trillion miles driven in China alone. 2 trillion miles, that's an enormous number of miles. Here in China, Didi is able to connect spare seats, extra seats, unutilized seats, which is an asset that is sitting in society that is not being utilized. Unutilized seats connected to someone who would like to go somewhere. Basically, a ride that has almost no cost. The car already exists, the seat already exists, but using artificial intelligence, they could recommend the right car to the right driver to the right rider, and then make the recommendation or predict or regress what is the fastest time of arrival and what is the best path to the destination. That's an artificial intelligence problem. Support the ever-increasing volume of transportation and mobility. Manufacturing, $5 trillion are manufactured here in China each year. If the equipment was down just 1% of the time, or even, let's take even a smaller number, if the equipment is down only 1/10 of 1% of the time, that's a $5 billion loss. $5 billion loss. $5 billion, that's the size of a large company, lost simply for no reason. Wise Engine, an AI company, could do predictive maintenance. So they know they could learn. Their machine can learn. Their machine learning systems can learn when a machine is about to fail. And before it fails, you can go and take it offline in a methodical way to affect manufacturing as little as possible. The benefits in manufacturing is quite extraordinary. Well, it turns out the entertainment industry here in China is really big. The number of movies made every year is growing, and most of the movies are rendered in using GPUs and software. Now using artificial intelligence, we could accelerate the rendering and the making of those movies and take pressure off of all of the studios so they could make more and more beautiful movies. Artificial intelligence has impacts across the world's largest industries. And the impact is always measured in tens, hundreds of billions of dollars. And the reason for that is because artificial intelligence applies to big data. You need to have a lot of data to be able to teach an AI. And each one of these industries, from healthcare to transportation, logistics, manufacturing, to e-tail, these are all data-driven companies. They can now take their data, teach an artificial intelligence network to predict a better outcome so that they can optimize their business. Artificial intelligence can learn, but artificial intelligence can only learn with a lot of data. AI is going to change the future of computing. AI is going to change the future of computing not just in how it's used, but how it's designed. Let me now talk to you about that. AI is going to transform computing altogether. There are two types of computers today, and they're very different. They seem the same, but they're radically different. On this side, what some people call supercomputers or high-performance computers are computers that are designed for very few jobs, but very large jobs. The jobs will run, the simulations will run for many days, potentially many weeks, and some for many months. These are gigantic simulations. They're gigantic simulations of a fusion reactor, or it's a gigantic simulation of a molecular dynamics, a particular virus. It could be a gigantic simulation of weather to try to predict climate change. Gigantic simulations. Few jobs, very gigantic ones. And this is hyperscale. This is came out of the birth of the internet, and this is about serving hundreds of millions of users with very small jobs. Hundreds of millions of small jobs. These markets these architectures are going to be fundamentally changed by AI. And so this is scientific computing where it started. Few users, big jobs, tens of thousands. In the case of the summit, 27,000, tens of thousands. And this is hyperscale. It was created for search. Small search queries on large distributed databases. The formation of Hadoop and MapReduce made this possible. This particular data center is called hyperscale. Millions of CPU nodes, weak nodes, small nodes, running in a data center in a distributed system way. Most of them are not working together. This serves hundreds of millions of customers. This serves tens of customers, tens of users. These two machines are radically different in architecture. Strong nodes, tens of thousands. Weak nodes, millions. In the future, and today is future, in the future, these machines will also be called upon to do machine learning, data science, and AI. And the reason for that is this. Scientists have discovered that AI is fantastic. It's fantastic to fuse with simulation techniques so that they could use and analyze much, much bigger models. Simulation and prediction combined is a new method of computing. Data science and scientific computing coming together. Deep learning and scientific computing coming together. Machine learning, data science, and deep learning and simulation coming together. And so that's the first trend, is that scientific computing will include machine learning in the future. The second trend is that developers are going to need these high-performance computing systems in the future. And the reason for that is because we needed to write software. Software developers are going to need supercomputers in the future. Every company that develops software will need accelerated supercomputers in the future. Our software engineers now have thousands of these systems so that they could develop their software. And the Michael Jackson dancing I was doing was trained on a system like this, on a high-performance computer. And so in the future, the developers are going to also include data scientists and AI researchers. And as a result, supercomputers will go from scientific computing from the research labs out into companies and out into internet companies. On the other hand, in hyperscale, what started out as queries is now internet services that are only possible with machine learning. And machine learning, as you know, requires large computation, a machine that is very, very strong. And so the method is to take many of these hyperscale nodes and combine them to work on one job. Instead of many jobs running on one node, in the future, it will also have one job running on many nodes. And so hyperscale will also become a high-performance computing system. The second dynamic is that it used to be used primarily for the internet services, but in the future, this infrastructure will also be open to the public for public cloud. And the public cloud users will be AI researchers, it'll be data scientists, it'll be scientists, and they will need this hyperscale data center to also be an HPC. So the point is this. Supercomputers are going to become AI computers. Hyperscale data centers with millions of weak nodes will also have to become high-performance computers. Both of these systems are changed because of AI. And so we created two system architectures to be able to enable both of these systems to be able to enter the world of AI, to enter the world of machine learning, and to enter the world of data analytics. The first is what we call the HGX-2. The HGX-2 is designed to be a very, very powerful computer. It is designed to be able to process both scientific codes as well as AI codes. It is able to process large amounts of data. On the other hand, we have a little tiny computer. It's powerful, but it consumes very little power. We call it the NVIDIA T4. I'm going to tell you about the NVIDIA T4 in just a second, but let me first tell you about the HGX-2. 哦，哇，蛮重的。I think this is maybe 400 pounds. Just the limit of my lifting. There are 8 processors, like this. Okay? So 8 processors like this. They're all connected together using NVLink, 300 gigabytes per second, connecting every single GPU to every other GPU. So everybody can talk to everybody at the same time. Each one of our GPUs has 32 gigabytes. So together, this motherboard, this system board, has 256 gigabytes. 256 gigabytes for the engineers in the room with a bandwidth of 8 terabytes per second of bandwidth. So this is 1 petaflops, 8 terabytes per second of bandwidth, and 256 gigabytes of memory, all working together. Okay? This is like 400 servers. 400 servers will require this whole stage replaced by this computer. But wait. You know that your data scientists and AI researchers are the most sought after engineers and the most valuable engineers you have right now. This is their tool. This will improve their productivity from hours, from days to hours, from days to, 太重了. From days to hours. Would you like to try? 重吗？好重啊 ！Yeah. Oh. Did you work out today? You don't need to now. 不需要了。Okay, so your AI researchers are so valuable. They're so rare. So we want to give them the best possible instruments so that their productivity, so their research could be the most impactful. Okay, so this is the HGX2, and it is an incredible computer. Two of these fit in here. 2. So that we now have 512 gigabytes, half a terabyte of memory, 2 petaflops of computing, and 16 terabytes per second of bandwidth. This is just an amazing computer. And this is designed for high-performance computing to maximize the productivity of AI researchers, data scientists, when they're doing very large model training. Second. May I take a break? Getting old. Okay, so HGX2. I'm so happy today that the computer leaders of China has adopted the HGX2. This computer will advance the work of AI researchers everywhere. And from Baidu to Tencent, Huawei, Inspur, Lenovo, QCT, Sugong, Supermicro, I want to welcome all of our partners. I want to thank you for your support. All of you have worked so hard to bring HGX2 to market. Thank you very much. So that's HGX2. Designed to accelerate high-performance computing, designed for big data analytics, machine learning, deep learning, as well as scientific computing, designed for engineering departments, AI research departments that needs to have the best possible tools and the best possible instrument so that they can get their jobs done. Once you develop the software, the software is run in a data center. That's called inference. Training is the development of the software. AI is writing software. That's called training. We're teaching the AI how to write software. The second step, when the program is finished, it has to run in a large data center, and that's called inference. To make inference, to infer, to predict, to classify, to regress. All of those statistics words basically meaning to make a prediction. We created our first generation inference chip, inference GPU for hyperscale data center. It was introduced last year called the P4. And we were so successful launching the P4. So many users. They're using it for large-scale speech recognition, large-scale speech synthesis, image recognition, fraud detection, anomaly detection. So many different applications. And the applications just keep on growing. This year, we have something really, really special. And it's called the NVIDIA T4. The NVIDIA T4 is really small. It looks very big over here, 可是很小的。你看得到吗？很小的。It's like a candy bar. 70 watts. Only 70 watts. Less than the power of a CPU. Less than the power of a CPU. But about 300 times the performance for deep learning of a CPU. Less than the power of a CPU. Less than the power of a CPU, but several hundred times faster. Compared to P4, look at this is already much faster than a CPU. And look at a T4 compared to a P4. In just 1 year's time, the T4 gave a huge boost. The T4 is 4 times the training performance. The P4, this was not very good for training. This was not very strong for training. However, the T4 is universal. You can use it for training, you could use it for inference, you could use it for images, sound, video. You could use it for almost anything because it is now so powerful. It's 4 times the training performance and 5 times the inference performance of the last generation, which was already state-of-the-art in just 1 year's time. T4 is also not just the highest throughput, it is also the lowest latency. The latency is so important because in the future, the internet will change. Today, you say, 谁的宫保鸡丁最好吃的? It will come back with a list of restaurants. It's a search result. In the future, it will in fact tell me. In the future, it will understand my speech. It will do natural language understanding to understand what it is my meaning. And then it will understand me because it knows that I am Suzhou, that I enjoy spicier versions of the food, maybe where I am, and it will recommend the best restaurant in that area, recommendation systems, and then it has to synthesize the speech. 4 neural network models just to answer the question, 谁的宫保鸡丁最好吃的? Has to be very, very fast. So in the future, the latency of neural networks has to be very fast, which is one of the reasons why we achieve the highest performance, the lowest latency ever recorded. The lowest latency ever recorded for deep learning. Incredible performance. Now, lastly, this is just the performance. This is the processor, the performance for training, for inference. But the most important part that people always forget is the software stack of today's machine learning, the software stack of AI is so complicated. It is so complicated, and it includes so many things. First, of course, is on this GPU, CUDA, cuDNN, TensorRT for optimizing compiler. We're now TensorRT 5.0. We can compile, optimize CNNs, RNNs, MLPs, so many different types of models. There are now thousands of species of deep learning models. We can now compile so many of them. And then we have to run it in a data center. The data center is complicated, as you know. Essentially, Kubernetes, which is a data center hyperscale workload orchestration system. Customers, users are bombarding a data center with a bunch of requests. Kubernetes has to figure out which one of the servers are available and where to put the job. And to manage the entire data center of millions and millions of nodes, of CPUs and memories and GPUs and storage and NICs, to manage all of that gracefully, optimizing throughput, optimizing utilization. And by optimizing utilization, you can improve the throughput and reduce the cost of the data center. Kubernetes is a very large-scale piece of software. On top, the applications are all in containers. And then on top, inside the containers, are what is called pods. And inside these pods, there are many different types of containers. And these containers has many different types of AI models. We want to be able to run many AI models at the same time on top of Kubernetes inside a data center for our GPU. Many models, anywhere in the data center, maximizing the utilization. This entire stack is possible with what we call the TRT inference server. It's a server software that sits on top of Kubernetes inside a container. Today, we are open sourcing this incredible piece of software. And so TensorRT inference server, you can go to the NGC cloud registry for NVIDIA and you can pull it down. It is open sourced. Well, before we get there, Ryan and I are going to give you a demonstration of the new T4. But this is amazing. This only started production 30 days ago. 30 days ago, Turing T4, NVIDIA T4, went into production. What we're demonstrating to you today is running in the Baidu cloud. Okay, this is in the Baidu cloud. Ryan, why don't we just start?
Sure. Well, we're starting with CPU. So we simplified a service in the data center.
Do any of you recognize this demo from last year? Okay, we'll show you this year's demo, okay? Unbelievable. This is last year. This is, of course, CPU running at 5 frames per second. And Ryan and I, every single year, we promise that we will learn a new flower. Every single GTC. What is we learn B-bomb, right? Where's B-bomb?
Well, it might get lucky to show up, but we just saw Tiger Lily, and by the way, I saw it first.
Oh. Okay, so last GTC we learned Tiger Lily.
B-bomb, right there.
Oh, where? B-bomb.
Yeah, it was in the corner.
Oh.
We missed it.
Okay, all right. So we now know 2 flowers out of the several 100,000. A few more GTCs and we'll be ready to go. Okay, so this is CPU running in the Baidu cloud, right? Okay, go ahead. Let's now run T4. So you're running 4 T4s, is that right?
Yep.
Is that 4 T4s? So 4 T4s, if we said, we rounded up to 6 images per second, 6 images per second, so it's 1,000 times faster. 1,000 times we have 4 GPUs, so 250 times faster. Okay? So this beautiful little piece of amazing technology is 250 times faster than a CPU, and it's currently in the cloud. But here's the beautiful thing. If you have Kubernetes, did I go too far?
No?
Can I, how many more can I get?
Oh, you can get lots more. So if
Baidu has more?
they have lots more. Let's add some.
Wow. Baidu has a lot of computers. Ladies and gentlemen, the Baidu cloud is like completely elastic. If I need more, just buy more. Just buy more. Can we buy more?
Oh, that's all we got this time, but we can always add more.
We can add more in the future?
Yeah.
I thought you had 20 something.
Oh, there's 28. There's some waiting.
Can I get more?
Oh yeah, let's scale this up a little bit. So when our demand increases, we simply add more GPUs.
How 快，好便宜呀！ That's the only Chinese I know. 太贵跟好便宜 that's all. 好便 it means very inexpensive, very affordable. It's so good. Okay, so it's so easy. Our GPU, this T4, look at this. This, ladies and gentlemen, is a high performance computer. Okay? So this DGX is a high performance computer. This is designed for maximum performance, very big job, few users. This is a hyperscale computer. This is what a hyperscale looks like. This goes into hyperscale data centers all over the world. And it's so great. If you have any problems, you just pull it out. Okay, so this is 2 NVIDIA GPUs, like that. Only 150 watts, 70 watts each. This is like a laptop. This is like a laptop. And then you take this, like a laptop, you put it in here. And here is the CPU. Okay? And all you have to do is put it in here. Just like that. Step 1. Step 2, you go to the NVIDIA Cloud Registry where all the software is all containerized and Kubernetes is already developed. You pull the container. Step 3, you open an instance on the Baidu Cloud. Step 2, step 3, either one. Step 4, enjoy. Okay? Only 4 steps, so easy. Just like that. Now, this is the hard part. Of course, this computer, if it can only run one job, one type of job, it's not a very flexible computer. We would like this computer to run any machine learning model, any deep learning model, because we want to maximize the utilization. If we maximize the utilization, the cost will go down. Does that make sense? Okay? So we want to increase the utilization. The only way to increase the utilization is to be able to run multiple models of different kinds at the same time. So this is what Ryan's going to show you next. It's called the TRT Inference Server.
Absolutely. So let's switch over to that one. Here we go. So this is before the TensorRT inference server. You can see the same flowers demo, and that's the blue line on the graph on the right. And that is being run on those two, I'll use the mouse here, and you can see these GPUs are being used to run the flowers model right here. So this load for the flowers model is being used on those two GPUs. And then we have 3 other models running in the background. You can see the green, the yellow, and the orange curves. Those are 3 other models that are running, each on their own dedicated GPUs in the data center.
So you guys see that? So one model, this server can only run this model, blue. This server can only run green models. So maybe, for example, speech recognition. This can only run maybe product recommendation, okay? And this maybe only can run speech synthesis. So each one of the server is a dedicated appliance, not a general purpose computer, a dedicated appliance. Now the problem is, as Ryan was saying, the workloads can change. The data center is so big. There are millions and millions, hundreds of millions of people using hyperscale data centers all over China. The workloads can change. And sometimes, depending on the time of day, sometimes because of a special event, sometimes it's, a very special actor came to town or something, okay? So something happened that caused the utilization to change. And so here's...
Yep, let's spike the utilization again. So flowers got very popular, and our network just took a little bit of a... So we do these live. Let's hope it comes back.
It's okay. If it doesn't break, we know it's not live.
Here we go. That's back now. So here we increase the demand to 5,000. And so you can see that we're only able to deliver, with these 2 GPUs, about 4,300. And so you can see those 2 GPUs spike up to 80, 90% utilization. But we really want to serve more
You see
more
this?
requests.
You see this? So this workload is almost 100%. And these servers are not being very utilized. 15%, 16%. 浪费钱. Right? This is oversubscribed. That is undersubscribed. And so we need to create a system. We need to, number 1, we have to have a processor that can run any model. Number 2, we have to have a compiler that can optimize any model. Number 3, we need to have a container system, a Kubernetes container system, and a server system to run every model, any model, at the same time on top of one GPU. Very complicated. However,
along comes the TensorRT inference server. So we designed this server to be able to host multiple different models, all simultaneously on the same process. And so here, when we switched over, you can see now we've asked for 5,000. We're getting 5,000.
Everything is running everywhere now. Blue, orange, green, yellow. Look at that. Everything is running everywhere. Everybody's utilization is nominal. Go ahead, Ryan. No, keep going. Sorry.
Yeah, and of course, it gets better. So when loads spike, just like we saw before, it automatically just balances out over all the different GPUs that we have serving it. So you can see we spiked up the load, and that load gets distributed out nice and evenly across the board.
Wow. 84%.
It takes a little bit of time for the big one to
刚
catch
刚
up.
是浪费钱，现在是赚钱。
Oh, our network's kind of slowed down a little bit.
Uh-oh. Now is the quality of service issue.
Right? Come on, network.
Look.
There we go. It's getting better.
Adaptive, and dynamic workload balancing. And so in order to balance the workload across your data center, first of all, every single GPU, every single computer has to be flexible. It has to be flexible. It has to be programmable. Okay, Ryan, good job. So that's the NVIDIA T4, our first hyperscale GPU. Training, inference, any model fits easily into the hyperscale system. TensorRT inference server on Kubernetes, all of the software integrated. It's open source, and we can work together to integrate these GPUs into data centers. The T4 went into production just 30 days ago, and it is already the fastest adopted GPU, server GPU, in the history of our company. I am so pleased to see the world's leading system makers and internet services adopting T4 so quickly. From Baidu Cloud, Tencent Cloud, JD Cloud, iFlyTek, to system makers, H3C, Huawei, Inspur Power Systems, Lenovo, QCT, and Sugong. I want to thank all of you for your support. So, system architecture has changed as a result of AI. We are fundamentally re-architecting high-performance computing, adding new types of instructions so that Tensor Core for AI, multi-precision processing Tensor Core, and the ability to connect these GPUs together into one large system. AI processing, large memories. And on the other extreme, adding NVIDIA T4 into hyperscale to boost up the performance of the hyperscale data center. There's a new piece of software that we recently announced called Rapids. AI is not just deep learning. So far, everything I've shown you is deep learning. But AI is not only deep learning. AI includes machine learning. In fact, the vast majority of the world's industries use machine learning. Machine learning is relatively easy to use. Most people have the data from their operations or from collecting from their environment. They could use data processing, ETL, to prepare the data into tabular formats, into columns and rows. They could take that columns and rows data format and discover the necessary features called feature engineering. Once they're done doing the feature engineering, they could run that into a machine learning algorithm called XGBoost or K-means or random forest or doing regressions and classifications. That traditional method, classical method of machine learning is popular all over the world. In ad tech, internet companies, e-commerce, financial services, healthcare, machine learning is the most popular method of AI. Unfortunately, this method of AI has not been possible to accelerate. And the reason for that is because it was created in the time when Moore's Law was still progressing very nicely. The size of data was pretty small, and Hadoop and MapReduce were sufficient. Along came larger and larger and larger data, and people realized that the terabytes of data, not gigabytes of data, the terabytes of data, or the hundreds of gigabytes of data that they're now required to train the model with are simply too gigantic, and has motivated them to look for acceleration method. We worked with the world's leading open source community that created today's machine learning platform to engineer a completely from the ground up stack that enables us to do acceleration at the limits. It starts with the creation of the Apache Arrow. If you haven't had a chance to look at that, it is a vital piece of computer science work. It is columnar data, it is vectorized, and it could communicate between different applications using IPC. No memory copies, just inter-process communications. Just passing a pointer, and all of a sudden, this entire memory can be passed to another application. Apache Arrow is foundational to the future of data science. This is a very big deal. The second piece is Dask, the ability to turn large clusters of hyperscale computers into one gigantic computer, scheduling it, distributing the work, orchestrating the work, aggregating the work, reducing the work, being resilient. That capability of turning an entire data center into one gigantic essentially computer, is a really powerful thing. That is called Dask. On top of these two foundational innovations that we worked with the open source community on, we then built the rest of machine learning. Built on top of CUDA, we have CUDA data frames, which is Pandas-like. Pandas on Python is the single most successful, most popular data science library in the world. Pandas is essentially the programming tool library of data scientists. They're used by data scientists in all different fields, from biology to chemistry to genomics to ad tech, to you name it. Millions and millions and millions of people use Pandas, created by Wes McKinney, who wrote the Pandas library and built it on top of the NumPy library, which was created by Travis Oliphant. These two giants of the computer science industry created basically Pandas. It is now accelerated on top of cuDF, on top of CUDA, on top of Apache Arrow. cuML is a machine learning library of algorithms. It is like scikit-learn, the most popular machine learning library in the world. Scikit-learn, its algorithms and models are replicated in cuML. One of the most important ones is XGBoost, boosted gradient trees. Incredible performance. I'll show you in just a second. And then lastly, if you're using graph models, we have cuGraph. The wonderful thing about this is because everything is built on top of Apache Arrow, and Apache Arrow has connectors into other applications that can support Apache Arrow connectors. For example, PyTorch, you could connect the output of this work directly into PyTorch and enter into deep learning. And so we have cuDNN and deep learning frameworks that will be connected into this platform. This now becomes, from the ingesting of data, from taking data from storage, from CSV data, comma-separated values, we could load the data into Apache Arrow. You could do ETL on that data. Hundreds of gigabytes of data that you can process in just seconds. And then you could do machine learning on it in Apache Arrow by simply sending an IPC a pointer, or you can go directly into deep learning. Okay? So this is the NVIDIA engineered Rapids machine learning platform, data science platform. We open sourced this entire platform. And the success of that open source, the enthusiasm behind it is just fantastic. We're working with data science platforms all over the world. We've open sourced it into the community. People are plugging it in and connecting Rapids into their own work. Startups are integrating Rapids into their platforms. Large enterprise data science systems, whether it's IBM's Watson Studio or Oracle's or SAP or SAS, some of the world's most successful data science platforms can now plug in this accelerated data science SDK we called Rapids. And in the future, with all of the cloud machine learning platforms basically supporting Python and scikit-learn, we can now accelerate all of their machine learning services. And these are examples of the ones that we're working very, very closely with now to accelerate the delivery of Rapids into their services. You can see Rapids and machine learning, accelerated data science is literally going to be everywhere. This is probably one of the most important pieces of work we've done in the last 3 years. There are so many in the world who cannot benefit from deep learning yet. They don't have enough data, or they don't have enough expertise, or they just simply don't need it yet. They can take advantage of accelerated machine learning. This is an example. I won't run this example for you because it takes so many hours. This is, in fact, the perfect example of why data scientists' life is so painful. They spend their whole life waiting. This is an example. This is an example of the Fannie Mae loan data over the last 16 years. That data has every single month of whether you pay back the loan or you did not pay back the loan or you're delinquent on the loan. It has it for millions and millions of people over 16 years. 280 gigabytes of data. 280 gigabytes of data. Imagine your spreadsheet, your favorite and largest spreadsheet, is maybe a few hundred kilobytes large, maybe it's 1 or 2 megabytes large. This is gigabytes large. 280 gigabytes large. First, you have to read the data into the computer. Second, you have to run ETL, joins and group bys. You're doing feature engineering on a very large spreadsheet. On 20 CPU nodes, it takes 2 hours. 2 hours on 20 CPU nodes. On DGX2, that one machine right there, it only takes a few minutes. It only takes a few minutes on the DGX2. It takes 2 hours on 20 CPU nodes. This is running Spark, which is a distributed computing system. And with 50 nodes, it's still almost an hour. And 100 nodes, it gets faster. However, this is machine learning. This is actually XGBoost. Because the communications overhead of machine learning is so high, even as you increase the number of CPUs, the scale factor does not improve because you're now spending too much time communicating between the CPUs. On a DGX2, again, it takes a few minutes. In combination, from 3 hours to just a few minutes. From 3 hours to just a few minutes. Think about the acceleration. It is utterly crazy. Now, of course, this is only possible because of all the open source engineers that worked with us, all of the data scientists around the world that worked on these frameworks, and now we have Rapids, an accelerated data science platform. But you know what? This is what we really care about. This is how many servers it would take to do data science in a few minutes. Ingest, ETL, machine learning. If you want to do it in just a few minutes, it would cost 300 servers, $3 million, and 180 kilowatts. 180,000 watts. 180,000 watts. Basically, 2,000 light bulbs. 2,000 light bulbs of power. Well, if you had this, or you could do it this way. Before, after. Without me, with me. Okay. 你看了那么便宜的东西 As you could see, the more you buy, the more you save. The more you buy, the more you save. 太便宜了。 Incredible. I love this. Before, after. We have been so successful with Rapids already in China. It came to China literally just a few weeks ago. It was released in open source just a few weeks ago. It's been downloaded, and it's being used by some of the largest machine learning practitioners in the world. Ping An is the example that I was talking about earlier of their AI doctor. 8 billion people go to the hospital, but with Ping An's AI doctor, it's possible to train a neural network so that it could diagnose some of your simpler symptoms so that you don't have to make a trip to the doctor. BGI is using it for cancer immunotherapy discovery. Immunotherapy is basically directing your own immune system to attack the cancer virus. You have to first figure out the pathway of that cancer. And then you have to figure out which one of all of your natural systems, in combination with a vaccine, could open up that pathway to the cancer so that your natural viruses can attack just that cancer. Well, the classification of all these different what is called peptides, amino acids that are used in this vaccine, there are millions and millions and millions of them. How do you figure out which one of them will open the pathway, allowing your immune system to attack that cancer without the cancer protecting itself again? Well, using XGBoost, they're able to take something, the classification process, from hours to minutes. And so they could discover new vaccines much, much more quickly. Ping An is able to use XGBoost now to make predictions of epidemic disease so that it is able to figure out that there's an epidemic and alert the public as soon as possible. From hours to minutes, from hours to minutes. And so now machine learning can go from hours to minutes. All of this, as I've mentioned before, is software. We now have a full software stack for science. There's 600 different applications in the world that are now accelerated. We have science, data analytics, as I mentioned, QDF, deep learning, all the different frameworks from TensorFlow to TensorRT to PyTorch to Caffe to MXNet, machine learning, XGBoost, and all of the other machine learning algorithms that people generally use, from random forest to k-means to k-nearest, will be coming. Hyperscale inference, our inference server, all of our TRT runtimes, the containers, and then, of course, visualization, all put into the cloud. All of these applications are now containerized, optimized, containerized, and put into this cloud, and you can pull it. It's open. You can pull it, register, pull it, and run it in any cloud or any system vendor, system maker that is certified. We work with system makers all over the world to certify their computers to run optimally as well as with good reliability all of these software stacks. Today we're announcing that in China we have Huawei, Inspur, Lenovo, and Sugong as the first NGC-ready partners. So thank you very much for your hard work. NGC-ready systems. Well, the HPC market, HPC has been redefined. What used to be scientific computing, because of AI, is going to now include hyperscale data centers as they use AI on their hyperscale clusters, and enterprise as they use machine learning to become a data-driven company. Each one of these industries did not used to be a high-performance computing company. In the future, as more and more companies utilize machine learning, enterprises, hyperscale, as well as supercomputing centers will become high-performance computer industries. We will create computer architectures so that machine learning, AI, data analytics can pervade and can be useful in each one of them. Today, I showed you several things. I showed you that with our HGX2 system, we can address scientific computing. we can address scientific computing, bringing AI to the traditional high-performance computing market. I showed you that with Tensor Core GPUs, we've been able to bring AI to the internet companies. Our Tensor Core GPUs have been so successful. And then now with the NVIDIA T4, we can apply inference, and we could put GPUs into large-scale hyperscale data centers and turn those hyperscale computers into HPC. And then lastly, because of rapids, we can now bring machine learning, accelerate machine learning for all of the companies in enterprises and industries like healthcare, like retail, like financial services. This is the new HPC. What used to be a much, much, much more niche supercomputer industry, because of AI, has now gone into every industry. It makes sense on first principles. And the reason for that is because AI is about computers that write software. And it stands to reason that it takes a high-performance computer to write software that no humans can write, to learn from so much data and write software that is incredible. This is the new HPC. It is scientific computing, it is data science, it is AI. I've got some fun demos for you. This is the last chapter. AI, computing, AI automating the world. Everything that moves in the future will be AI. In fact, it's just some amazing statistics I'll share with you in just a second. In order to enable this future of AI coming out of the clouds into the world, and for these machines to be working among us, cooperating with us, helping us do things, moving about by itself, we need a special type of new processor. That's why we created Xavier. Xavier is a first of its kind. And this Xavier processor,等一下子，我自己来拿，我马上回来。Where is it? What could go wrong? This is what happens when we have no rehearsals. This is an Xavier processor. This computer is complete right here. This is an entire computer. Amazing computer. This is something along the lines of a few hundred laptops of AI processing capabilities. Several thousand engineers worked on it together at NVIDIA. This is now in full production. The world's first AI computer designed for autonomous machines. This is the Xavier. It's actually amazing. 7 different types of processors. Those 7 different types of processors is necessary to compute the pipeline of a robot. This is the pipeline of a robot. First, it has sensors of all different types. It could have cameras and lidars and radars and sonars, all kinds of different types of sensors. We have to process the sensors. Depending on the sensor type, the processing is very difficult using a different type of processor. Maybe it's a stereo processor. Maybe it's an image sensor. Maybe it's a video stream. Maybe it's images that are coming in that has to be denoised or warped. Tensor Core, CUDA, is used for perception, recognizing the environment. Then you have to do path planning. How do I achieve my mission? If my goal is to pick up this, how do I achieve it? And then lastly, you have to perform the action, to actuate the action. Okay? So the processing is very complicated. It's very unique. And it's the first time in history we've been able to put it on one chip. And now Xavier is in full production. Xavier plus our GPU is created to enable a scale of family of computers from one single chip to all kinds of different configurations for more I/O, more sensors, and more processing, depending on the type of application. Maybe it's a delivery robot. Maybe it's a medical imaging system. Maybe it's a driverless taxi. All of these different types of applications have different types of requirements for computing. And so we created a scalable family, and now we can address all of these applications. However, software is the key to success. These computers is just the starting point. Because they're so complicated, the software on top of it is equally complicated. And so we created 4 computing stacks. The 4 computing stacks are: one for medical imaging, applying classical medical imaging, image reconstruction, and then applying AI to it, we could do detection of anomalies in real time. We could use it for streaming analytics, whether it's camera or pressure sensors or vibration sensors or sound. We could use it to stream data from all over the world's IoT and to be able to infer and make predictive analytics on that. Indoor or slow-moving, unstructured environment robots. We call that Isaac. And then there's high-speed, life-critical, but structured driving. We call that form of robotics the self-driving car. Each one of them comes with a 3-layer stack. Our platform is open. You can have layer 1, which is the core OS with all of the APIs implemented. This is absolutely world-class at our company because of our long history of professional and high-performance computing applications. The second are acceleration libraries. These algorithms are really well-tuned. Takes advantage of all the processors inside this chip and all of our processors to deliver the highest performance for images and signals, deep learning, video. In here, multi-GPU or virtual GPU for ray tracing, for accelerated linear algebra. And then on top of that, we have the platform software we call layer 3. Each one of the layer 3s are different. Some of the layer 2s are different, and most of the layer 1s are the same. This is Clara. This is Metropolis. You see again 3 layers. The basic layer of OS, the acceleration libraries, and in this case, a streaming pipeline framework. Neural networks and plug-in algorithms are piped from one application to another. This is the Isaac robot. And here, as you see, we have very similar core OS, very similar image processing library. However, for the application layer, layer 3, from visual odometry to perception to localization and mapping and planning, it's completely different. What you saw just now, you saw 2 versions of Isaac. One of them is a virtual reality simulator that Isaac learned how to be Isaac. We created a virtual reality simulator to teach Isaac so that Isaac doesn't have to run into my leg while it's learning how to be Isaac. So once Isaac is learned how to be a good robot, then we can set him outside, and Isaac did exactly the same thing. I am so happy to say that there are so much exciting development in these delivery robots, last mile robots, all kinds of autonomous machines of all kinds of interesting applications. There are 50, 60 billion parcels, 50, 60 billion parcels delivered in China each year. 50 to 60 billion parcels. You order online and delivers it to your home. That's up from 30 just 2 years ago. 30 to 60 billion, doubling in 2 years. The demand of home delivery is growing at Moore's Law. That was a joke. The demand is growing very fast. And so JD.com created their robotics lab. Have been working with us for a long time, and that we work together, and they're using our platform to create a last mile delivery vehicle. This is Meituan's. This is 小袋. Meituan is 小袋. Meituan delivers 26 million meals per day in China. Nobody goes out anymore. 26 million meals in home delivery in one day alone. They employ 500,000 people to deliver all of the meals to your home. Now they have 美团小袋. Hopefully one day, this cute little robot will bring your lunch to you. 菜鸟. Did I say that right? 菜鸟. 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 Also developing a home delivery system. I think this is going to revolutionize home delivery. It has to, because the number of people who are buying things online is growing exponentially, but the number of truck drivers and home delivery people is not enough. And so we must be able to supplement and take that pressure off using artificial intelligence and robotics. 2 trillion miles driven each year. And we have a stack again, Drive OS. This is very unique because this requires functional safety. This is ISO 26262 certified. This is fail-safe. It is very resilient and very complicated software at the OS level. We also have libraries, acceleration libraries, to take advantage of all of the processors in here so that the processing can be fast and low power. And we have the necessary driving stack on top. We created an open platform. This open platform can be enjoyed at level 1, layer 1. If you would like to write everything yourself, you can enjoy level 2 and then write everything above, or you can enjoy level 3 or parts of level 3. You could decide how you would like to mix and match. As a result, the number of people who could develop on this platform has expanded tremendously. We've been making a lot of progress in this area. I want to show you, every year when I come back, I want to show you some of our progress. This next demonstration, next video, is surround video. It's surround and surround perception. So we're recognizing, of course, what's in front of us, perceiving what's in front of us, the lanes, where we're going to drive, but we also recognize the surrounding vehicles, and we track them, and we visualize it in a bird's eye view. By doing so, you have great confidence that your car can see everything around you. That confidence is really important for you to trust the autopilot system. So the first demonstration is surround perception. Okay, surround perception. Now thank you. That is the building block of what I'm going to show you next. California, where Silicon Valley, where our home is, we're surrounded by several highways. One of them is called 280, the other one's 101, and then there's 92 and 85. And the highway is very complicated. And so we challenged ourselves to drive 80 kilometers, 50 miles from highway to highway to highway to highway without touching the steering wheel, basically from point to point across 4 highways. This video I'm going to show you is basically raw engineering video. You're going to see a lot of different networks, a lot of different neural networks, and it's very noisy. But that's the point. In order to achieve very high quality, you have to have many different types of neural network models, not just one. There are so many different models, and they're working together in a fused way, in an ensemble way. Basically, we have multiple points of diversity and redundancy, and they work together to achieve a good result. Just like a good company has diversity and redundancy, just like a good team has diversity and redundancy. In order to have a good system, a robust system, you fundamentally have to have redundancy and diversity. Okay, so what I'm showing you here is a whole bunch of different neural networks running at the same time, and most importantly, enjoy Silicon Valley.
Weather in San Francisco now?
The weather is 67 degrees and cloudy in San Francisco.
How about tomorrow?
There will be partly sunny skies with a high of 69 degrees and a low of 58 degrees in San Francisco tomorrow.
Gosh, this is fun. You know, for all the engineers in the room, this is just incredibly fun. AI, autonomous machines, so many great challenges, the type of things that we can finally do. Never dreamed that it was possible 10 years ago, and now because of AI computing, all of this is now at our fingertips. What you saw just now is a demonstration we just did recently. If you come to Silicon Valley, we'll give you a ride. This is NVIDIA Drive Developers Kit. All of this is in production today. You could get access to we call it Drive IX. Drive IX basically turns your car into an AI. You talk to the car talks back to you. All of the neural networks are in the car. It's looking at you. It's looking outside. And so this car, your car in the future will be able to interact with you, help you find places. Instead of typing in anything, you simply tell it where you want to go. Instead of asking a question about punching in the restaurant location, you simply ask it, where's the best restaurant? And then it takes you there. And so not only does it respond to you and interact with you and talk with you, it also makes sure that you are paying attention, that you are alert. In the future, level 2 cars will function incredibly well, just like a level 4 car, except the human is in the loop. The human being in the loop is vital to the experience and vital to the functional safety of the car. And so it has to pay attention to you to make sure that you're paying attention and that you're not falling asleep, that you're not reading your email, that you're continuing to pay attention and drive. It will also look out for you on the outside. If you're about to turn and run into another car, into somebody else's way, it will tell you that you shouldn't, or it might keep you from doing so. It pays attention to everything around you. So this car will interact with you, it will drive for you, and whenever you're driving by yourself, it will keep you out of harm's way. In the future, this system also is exactly the same system as our autopilot system that I just showed you. If you would like to develop on Drive, this kit is available today. I'm super excited to announce that the level 2 system that I just demonstrated, the capabilities that I talked about, will appear in a production car in the near future, in the next couple of years. This is a car that is famous for their safety, one of the most technically sound car companies in the world. They fame themselves on safety, and they have chosen the NVIDIA Drive AGX, the computer, as their next generation level 2 system. Here in China, the NEVs are racing to bring electric vehicles to market so that a large percentage of the future cars in China could be electric. We are partnering with some of the best: XPeng, Singulato, SF Motors. I want to thank you all for your support. Imagine these cars with the capabilities that I just described. We're also working with many companies in China on mobility services. From WeRide, Momenta, Too Simple, AutoX, Roadstar AI. 2 trillion miles. If those miles were more affordable miles, imagine the adoption of mobility as a service. If every single mile was delivered and it was average, pick a number of $1 for simple math, there's $2 trillion opportunity for mobility as a service here in China. Extraordinary. The trucking industry is also being revolutionized by AI. FTA, Full Trucking Alliance, FAW, the trucking company. And FTA, many of you know, is the Uber of trucks. It turns out there are they have 1 million businesses that they work with, 5 million trucks. Connecting businesses and trucks is a tremendous challenge in trucking here in China. In fact, most of the time, 40% of the time, the trucks are empty. There's so much waste that can be benefited from AI. And so FTA has created essentially the Uber of trucking to connect truck drivers to the cargoes. FAW plus AI and ourselves are working together to create an autonomous truck so that in the beginning, it could ease the challenge for truck drivers, and then long term, it might be able to drive a short distance autonomously, and then long term, more of it autonomously. Our ecosystem of autonomous vehicles is growing, and the number of companies that we're working with here in China is really quite fantastic. Volvo is a Geely company. Chery here in China, thank you very much. XPeng, Singulato. We have Momenta, AutoX plus AI, WeRide, FAW, Too Simple. One of our tier 1 partners working with us to take the technology to car companies all over China is Desai AV. We're super excited to be working with Desai as our top tier 1, Desai SV. Thank you very much, everybody. And one of our longest partners in the autonomous driving world is Baidu, both for mapping as well as utilizing the computer for their self-driving car stack. Now a car with the drive computer could be autonomous in the West as well as autonomous here in China. So really fantastic. One computer solving multiple software stacks connected into the ecosystem of different countries. Well, that's it. I talked about 3 chapters today. There's so much to share with you. I talked about number 1, Turing reinventing computer graphics with ray tracing and artificial intelligence. I talked about reinventing the future of high-performance computing, the new HPC. The new HPC includes scientific computing, data analytics, and AI. And there's 2 types of computers, from hyperscale to high-performance computers, that we have now brought AI capabilities into them. And then lastly, NVIDIA AGX family, Xavier processor, a computer designed for autonomous machines for robotics, is now in full production. And so car companies who are driving and racing towards autonomous capabilities and electric capabilities in 2020 and 2021 now have a processor they can ship into those cars. The industry is changing so fast, and AI is fundamentally changing all of it. And as you can see, we've brought AI into every aspect of our company, from computer graphics to high-performance computing to autonomous machines. This is some of the achievements from last year. I want to show you one more achievement from last year. And this particular demonstration is not a video. I want you to remember every single second while you're watching this, it is not a video. You got to keep saying to yourself, this is not a video. Everything about it, the lights and the reflections and the lasers and the shadows, are all being computed in real time. Everything about the materials, why metal looks like metal, why plastic looks like plastic, why glass looks like glass. Everything is being computed in a physically based photoreal way. And so what I'm going to show you is a Turing demonstration, but it is not a video. Roll it, please. NVIDIA Turing, 10 years in the making, reinventing computer graphics, available today. I have one more little surprise for you. And I want to thank all of you before I go, I want to thank all of you for coming to GTC. This is a record GTC. GTC was created for researchers, scientists, developers who either use computers to do their life's work or build computers as their life's work. This is where GTC has become the conference where science, artificial intelligence, robotics, and computer graphics is displayed at its fullest. I have one more little treat for you. And with that, I want to thank all of you for coming and have a great GTC. Thank you. 大家谢谢。